Mr. Evans, greetings.
Hey, Mr. Bailey.
Yes, sir. How you doing?
I think everybody getting confused about that. Are you using the same link?
Yes.
Okay. Yeah, they was. I just had a few people asking.
Hello.
Greetings, greetings. How you doing?
My mute button was fighting me. I'm good. How are you?
I'm all right. I didn't get washed away. Did get a little damp on the way in this morning, though. That's all good. If I didn't know the rain was gonna be so bad, we could have been on campus. I know y'all really want to do that anyway. Okay. So I think what we're going to do tonight is we're going to look at an example problem from scratch. Quick review of the stuff we covered last night. And then we're going to walk through the example that was worked in the book. And that will pretty much finish up the low frequency response stuff. I consider starting high frequency response, but on second thought, we'll actually do that next week. There's some theory I want to go through. Nothing that you'll probably ever have to see again, but I like for you to at least have the information. And then if you have to go back and look at it sometime in the future, you at least would have seen it. So I don't expect anyone to be heavily involved in doing analog circuit design, because the truth of the matter is there aren't that many people around who still do it. They're either retired or expired or expiring, or like me, just won't leave. So the company I work for now actually do a lot of analog stuff. They do they make equipment that's used to calibrate utility meters. And originally utility meters had the little wheel that was spinning as electromechanical. Now all that stuff is electronic. So there are people who actually design electronic meters, and the company I work for now designs the equipment they use to calibrate the electronic meters. So a lot of stuff is still very, very analog, although you have some digital stuff in there also. So it's not a bad skill to have. If I had to go back and do it all over again, I would do exactly what I'm doing now. And part of what I'm doing now is I'm continuing to learn. Because we got a lot of FPGAs that are going into products. People have moved away from microprocessors, not completely, but a lot of companies are using FPGAs instead of microprocessors or microcontrollers. It allows them to basically change the digital system configuration without having to basically spin another board. That stuff I'm also looking at too, just because it's part of the technology. So for those of you, and I know there's not a class at Jackson State, if I'm still around at some point, I might see if they'll allow me to teach it as a special topics, an introduction to field programmable gate arrays. Most schools, when they're doing their digital logic now, are not using chips the way you're doing in digital logic. They're actually using FPGAs. I'm okay with that, but I still like the idea of using chips because it gets you involved and hands-on. So you actually have a physical idea of what's going on, as opposed to just writing some code. You know, everyone thinks that you just write code and shit just fall out of heaven. Well, that's not the way it works. There's a hardware behind that code. But the way things are now, most people don't know anything about the hardware. They just think you just write the code and stuff just shows up. Anyway, uh, I'll get off that slight tangent. And let me pull my camera. And for those who are still joining, get here when they get here. Oh, I kill my video. Yeah, I'm going. It's been a long day. What I want to do is share. Give me 1 second. Okay, can everyone see my hand?
Yes, sir.
Yes.
Thank you very much. Oh, come here. Make my window a little bigger. And I want to go. Okay, I got the video going. Okay, so I'm gonna go back very quickly through this R-Thevenin stuff for these different capacitors. So if we have a small signal model that look like this, RB or beta times RE, if you want to call it that. GMBB. RC. CC. RL. Then we have a RE here. CE. And then over here we had our parallel combination of R1 and R2. I think the author calls it R big B. We can call it RB if we want to make it a little simple to write. Source resistance and then our signal source.
What about the RB capacitor?
Thank you. I was like, something's missing.
CB capacitor.
Yeah, I know what you mean. Well, yeah, I was like, something's missing here. Oh, that went here. CB. Thank you. So here's our small signal model, including all of our external capacitors that we add to the circuit for two reasons. One, they are decoupling capacitors. That's CB and C sub C. And 2, they have bypass. And that is CE. The other thing that CE does is increases the gain. And it does that by basically, well, it's a bypass capacitor. So it's bypassing RE and making this look like it's not here. And if we remember, our voltage gain was minus RC in parallel with RL. And I'm going to draw it with RE in there. Will RE plus RE. This is what the gain expression was if we didn't have this capacitor here. When we have this capacitor here, then this becomes 0. And our gain becomes minus RC over RL over little RE, which we could also write as GM RC in parallel with RL. And we can calculate our RE, the thermal voltage over the collector current. And yeah, so it's 1 over GM. So you can put a 1 over GM here in the, excuse me, a RE in the denominator, or you can multiply by GM here. It gives you the same answer. So these guys here are responsible for decoupling. It's basically preventing any DC voltage that may be present in our source here from adversely affecting our base current here. Keep it from adversely affecting our collector current here, DC wise. Okay. And this guy right here, basically it increases our gain by bypassing RE. The other thing these capacitors do is they determine pole location in the frequency response. So we're going to have a pole associated with CE, a pole associated with CC, a pole associated with CB. And the exact location of them depends upon the size of the capacitors and also the size of the Thevenin's equivalent resistance seen across their terminals, which we looked at last night. Okay, let me redraw this and then we'll do, so how do we determine our pole locations? Ooh, that's way too high, sorry. Pole locations for a circuit that has multiple capacitors. Okay. So number one, you choose your capacitor that you want to determine our Thevenin for. And two, you short all other capacitors. And then three, find our Thevenin for your chosen capacitor. And once you've done this for one capacitor, you short another capacitor and you put the other one back in the circuit and you just repeat this. So in the case of 3 capacitors, you have 3 R Thevenins. So let's see if we can do this quickly. Let me redraw the circuit over here. I'm going to put all the capacitors in, and then I'm going to pretend that they're shorted. Instead of redrawing the circuit every time. Okay. So let's pick one. Let's choose this one. So for CE, or Thevenin, it's going to be this resistance, RE, in parallel with resistance looking into this terminal back to ground. And so it's going to be RB plus RS in parallel with RB. Little RB plus RS. You would pretend that this was a short. And then for CB, R Thevenin, let's call it CB. This is CE. It's going to be what? The Thevenin resistance seen across these terminals here. The voltage source goes to 0, so it's just RS plus RB. And then for C sub C, R Thevenin, C sub C, here, you're going to have RS plus RL. Excuse me, RC plus RL. And I hope I got those right. Let's see, that's this in parallel with this plus this in parallel with that. And this is this one plus this one and this, yes. So here's the R Thevenin associated with each of these capacitors. And then the pole that's associated with each one, I'm just going to write in general, F is 1 over 2 pi R Thevenin X. Well, X is one of these times C sub X. Well, C sub X is the associated capacitor. So that's your pole location. Now, I think we had talked about, but we'll see in the example also. These all at different frequencies. So one of these will show up, well, let me stop it here. So this is the equations. This is our pole location for each of these 70 equivalent that's seen by each individual capacitor. So now we can get to a real circuit, plug some numbers in, and let's see what these actually look like. Oh, here we go. Will be a little long, but that's okay. So we are looking at practice problem 9-3 in the reading material I sent you. Let me get this straight, sorry. So there's our circuit, with all the components. Again, it's all straight out of the textbook. And so what they ask us to do is determine the low cutoff frequencies, basically 3-pole locations, the dominant cutoff frequency, we call SFL, the voltage gain, and we're going to assume that beta is 100, excuse me, 200. So let's see. The first thing we need to do is find our operating points. So VB going to be, oops, let me put the values in here. 7.5K here. And 30K here. It's going to be 7.5 over 37.5. And our supply voltage is 15 volts. For some value. And let's see. Here.
It's 3.
3. Okay.
3.
So 3 volts. I like that. Then VE is VB minus 0.7, which is what? 2.3 volts. Then IE, VE, RE, 2.3 volts over, was it 1.5K?
.66, or you want to do 1.67?
1.66 is good. I'm okay with either one. What's the units?
Million?
Milliamps. There you go.
How did you get the 37.5 in VB?
So voltage division, 7.5 over 7.5 plus 30. It's 37.5. The sum of the two.
Okay, thank you.
And that's the problem off of page 359, 9-3.
That is correct. Page 363.
It's on 363.
Yeah.
I'll follow
Problem
along.
9-3.
363. Okay, I see it now.
So what is that? So we have a VE. we can calculate our VC and all that stuff, but we really don't need it. We actually have everything we need right now. But you know what? Let's just do it anyway for good practice. So we got VC then would be what? VCC minus IC times RC. 15 minus 1.66 milliamp times 3.6K. It's good practice. It's like about 9.02 volts if I can still operate a calculator. So that gives us our VB, our VE, our VC, our IE and IC. If we want to calculate our base voltage, we can. Excuse me, base current, we can. So base current then is just going to be our collector current divided by beta, which is 1.66 milliamp divided by 200. Oops. So that's about, no, that's not right.
I got 0.0083.
Okay, in engineering notation, that would be what?
8.3
8.3, what?
milliamps.
Milliamps. Excellent. Okay, so it's all our currents, all of our voltages. So since we're here, no, let's start a small signal model first. Now, we always have to calculate some of these currents because we need the currents to get our GM or low RE, whichever we want to use in the equation. So now we have our small signal model. Well, let's do some calculation. Well, we'll do it in just a second. So we have, here's our base. Beta IB, GMVB, this is VB, this is RB. And we're doing a small signal model. So we're calculating our gain now. So what do we have here? All these capacitors can look like shorts. We call this RL prime. Well, RL prime is RL in parallel with RC. We'll calculate that in a second. Our emitter, because of this resistor, this capacitor here, this gets shorted to ground. So we have no RE. Over here we have a short for our capacitor. 1.5K. Our signal source. And what else we got? Here's how output node will be out here. Okay, so now our V out minus GM times VB times RL prime. Let's go ahead and calculate RL prime. That's just RC in parallel with RL. It's 3.6K parallel with 4.7K. It looks like about 2K, 2.03K. I got it right. Now, where's our, what else we have? We have this small signal parameter here, GM. GM is what? Same as 1 over RE. And so that's going to be IC, or your thermal voltage. Just IC over 0.026. So approximately 40 times IC. It's actually a little bigger. It's like 42.6 or whatever. But I'm being lazy. No, it's like 38.5. 0.025, 1 over there is 40. So instead of calling your thermal voltage 26 millivolts, I call it 25 millivolts. So I can approximate this is 40 times IC. So a GM then is 40 times IC. IC is IE is 1.66 milli. I think this is 0. Well, let me go ahead and put 1.66. Yeah, 66 millisiemens, which is 1 over resistance. So RE then is 1 over GM. You want to know what that is? It's about 15 ohms. Now, why do I need that? Because my little RB here is actually beta times RE. And beta is 200. So my RB here is going to be just about 3K, 0.01 K ohm. So here's my V out. Only thing I need to do now is what? Find my VB in terms of VS. Oh, I'm sorry. I left something out. Y'all didn't catch me. A big B, which is R1 in parallel with R2. So over here, RB is equal to R1 in parallel with R2. That's 7.5K in parallel with 30K. Looks like about 6K. Okay. So now we can find our input impedance, our RN. Our RN is just RB, big RB in parallel with little RB. So RN, RB, parallel with little RB. And that's what? 6K in parallel with 3K. See if I can do that in my head. That's what, 18 over 9 to 2K? Yep.
You're right.
So that's our RN. So now we can find the voltage VB. And it's just RN, or RN plus RS times VS. So if we plug this in for VB here, we get this following expression: V out is equal to our GM 0.066 times our VB. No, let's go ahead and finish this. So that's 0.066 times our VB. 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 So that's 0.0 2K over 2K plus 1.5 is 3.5K VS. So that's 2 over 3.5 times VS. That's my VB times my RL prime. My RL prime is RL in parallel RC, which is about 2K. And so now the definition of voltage is V out over my signal source V sub S. And so that's 0.066 times 2K times 2 over 3.5. And let's see what that comes out to be. If I did fat finger something. Well, to this, if I'm right about 75.4. So my voltage gain now then is, actually I should be saying the magnitude of it because it's a negative sign. 75.4 volts per volt, if you want to put units on it. So that's my voltage gain. So, any question about that?
How did you determine what VS was again?
I didn't.
Okay.
I didn't tell you what the value of VS was, but I know the ratio of V out over VS is this. So my gain is this. So whatever, well, that's a good question. So let me ask, let's go down that road just a little bit. I didn't tell you what VS was. I just found an expression of V out over VS and define that as the gain of my circuit, which is this, right? So now let's say we have a signal source, VS is 100 millivolts. What is V out? V out is the gain times the VN. So the gain is 75.4 times my input VS, which is 75.4 times 100 milli. Well, 100 milli is 0.1, so I think I can do this in my head. So then my output swing would be 7.54 volts. So I put 100 millivolts in, I get 7.54 volts out. Question. So where did I get that from? Right here. The gain is defined as V out over VN. So when I say the gain here is 75.4, that's V out, I'm sorry, V out over VS equals 75. V out, if I divide both sides by VS, it'll be 75. So now if I put in my value of VS, I can tell you what the value of V out is. What we've been calculating is the ratio, basically my multiplication ratio. If I put some signal in, how big does the output signal become as a multiplication factor? Now, if you tell me exactly what size signal you put in, 75 millivolts, 100 millivolts, I can give you a number as to how big the output is going to be. So over here, although the problem didn't ask for it, I say, well, let's assume that our signal source here is 100 millivolts. Come down a little bit. Assume our signal source here is 100 millivolts. How big is the signal here? And it's basically 75.4 times 100 millivolts, or the output will swing 7.54 volts for a 15 volts supply voltage. Okay. Questions?
I just keep getting lost, like somewhere in between, like when you do the small signal model down here somewhere. I just keep getting lost every single time.
Okay.
Like I get the other part when you starting it off, but I guess it's just so many to trying to find.
Well, actually, it's not that many. It's a step.
Yeah, I think that's just steps or something. It just
So,
keep confusing me every time you get down that way.
okay. Well, let me see if I can label them for you. So after we draw our small signal model,
Mm-hmm.
we write that V out is minus GM times VB. That's this control voltage, the current source here,
Mm-hmm.
times this resistance here, which we call RL prime, which is RL in parallel with RC. Are you okay with that?
Yeah, I'm okay right now.
That's step number one. Get an expression for our output. Now,
So are you gonna be on the test like the exams, are you gonna say find V out, or find each resistor, how you doing the RL, and
yeah,
you see what I'm saying?
you're going to have to find that in order to get an actual number, in order to get the gain.
Right. Okay.
So I can go back and just eliminate all the actual values themselves. And what we'll be talking about is just an expression like we did first class.
Mm-hmm.
Once we get the expression, then we substitute the number in for each one of those individual resistors or whatever. And that's how we end up with this. Instead of, where is it? Well, actually, kind of skipped a step and started um, adding some stuff together, because here I started with V out is, I put in the value for GM because I'd already calculated over here.
Mm-hmm.
And then I put in the value for RN over RS.
Okay, I see. Okay, yeah, right there. The GM, you put 66 what did you say, milliseconds, you said?
Siemens.
Millisiemens. And then you put the 0.06. Okay, all right.
We good so far?
Yeah, uh-huh.
So that's where, and then here's the voltage divider, RN over RN plus RS times VS. So all of this right here is VB. I just substituted this expression here, right here.
Mm-hmm.
And then the last part of it is what? Our RL prime. That's here.
Okay, now I see what you're doing. Okay, I see what you're doing now.
Okay.
Yeah, you see, okay, with the GM, then the RL. Okay.
So if you're ever confused by what I'm doing, please ask questions. I want you to get this stuff because it makes it easier on me. You know what's easier? The easiest paper to grade, easiest type of paper to grade?
A correct
Yeah. An A paper is easy to grade. It takes me less than a minute to grade an A paper. Now, some of them other things, I've gotten frustrated and just put stuff down and just walked away. An A paper is easier to grade. So, in a way, it's selfish for me to want you to make an A because it's easier on me. But it also makes me feel better that I know that you actually got this stuff, which is actually the most important part of it. So anytime you're not sure what's going on, feel free to ask. And also be aware of the fact that you ain't the only person with that question. You're just the only one who's bold enough to ask. So when someone says, hey, wait a minute, when you got there, I got lost, that's what I want to hear. Don't sit there and pretend that you're actually getting it when you know you're not getting it. And sometimes you just have to go back and walk through the steps after class is over. But then other times you need to ask in class. So what I try to do is to be very methodical. And I'll be honest with here, I kind of added a couple of steps together. Because what I normally would do would be to write V out equals, take this equation and write it here again. And then the next step, I was substituting in the numbers so you can see exactly where the numbers are going in this equation.
Yeah, I think that's what got me
Okay.
right when you just said. But I think once I like I say, when you get through, when we get done with the class, send the video to them. Like I said, I'm gonna keep going over to try to see what if I can catch it. But I mean, because that's what I had a problem with in electronics one. But
Okay.
yeah, so I mean, once I get to looking at the videos and keep seeing how you doing the steps, I'm eventually catch on to it.
I work it the same way every time.
Yeah.
Sometimes there's a little deviation. Sometimes I'll add a couple of steps together, but the flow is exactly the same. I always start with this expression for V out. When I do the small signal model, this is the first thing I write. And then I ask myself, okay, I have a VB here, which is this voltage. How do I get an expression for VB? Well, VB then is what? If this RB and this little RB, if I call it RN, it's just the voltage divider off of this right here, which is this. Now I can make it easy for you and say that RS is 0. If I do that, what's VB?
It's gonna be 0, right?
Nope. If I made RS 0, VB is the same as what then? Yes.
Okay, VS.
Ain't no voltage division. This voltage gets applied directly to this node if this resistor's not here. So then VB will be the same as VS. And so actually, let's look at something. Since we're here, where's my RN? Here it is. My RN is 2K. That's this looking into here. And this is 1.5K. So I can't say that RN is much bigger than RS because actually it's about the same magnitude. But this is a fairly large signal source here. This is usually something like 50 or 100 ohms. So if this was 100 ohms, and this is 2,000 ohms, I can make the approximation that VB is equal to VS, and I won't be off by much. But when RS is of a similar size as RN, I can't. I'll have to actually do the calculation. So that's like 2 over 3.5 is, that's not 1. That's something even. So actually, what this is doing is it's actually consuming some of my signal here. If I put 100 millivolts in here, and this was 0, or really close to 0, say 50 or 100 ohms, then most of this 100 millivolts will show up directly on the input here and get multiplied to show up at the output. But because this 1.5K is of the same order of RN, I have a voltage division here. So I may have 100 millivolts here. I may only get 60 millivolts showing up here on the input. So for the amplifier, what you really want is your input impedance to be much greater than this so that you're not losing any signal here. But in this particular problem, this is 1.5K. What you really want this to be is more like 50 or 100 ohms. But there's another way of dealing with that too, though. And in electronics 1, when I taught it, you would have to design this amplifier so it had a certain value, a minimum value of input impedance. Well, the input impedance is R1 in parallel with R2 in parallel with RB here. So you would have to choose these values of resistors here and choose your currents to give you a large input impedance compared to your RS. So the thing with analog design is it's not like digital where it's like one thing or the other. It's actually an iterative process, and you have a lot of degrees of freedom. I may say, hey, design me an amplifier with a gain of 100, and your supply voltage, it can be anywhere between 10 and 15 volts. That's a whole range of things you can do with 10 to 15 volts for your supply voltage, and still calculate and still get an amplifier with a gain of a minimum value of 100 or whatever I asked for in the specification. So there is no one way to do an analog design, because the power supply could vary, your load resistance could vary. I say I might just say that the gain has to be at least 100. You might decide to make it 200, or you might decide to make it 150. And so you have a lot of degrees of freedom when you're designing analog electronics, which is why I like it, because there is no one design. They may all have a similar architecture, but the actual values will change. If you look through the book, when you see you see this BJT amplifier, you'll see these values are not the same for every circuit they show you. They're different values. One of the things that what these do, if I make these resistors bigger, I reduce the overall current consumption in this circuit, because there's current flowing through here that that's not being used really, other than just to set this voltage level. So if I had this as so it's 7.5K and a 30K, that gives me a certain value. But if I wanted less current flowing through here and the same voltage, I can make each one of these 10 times bigger. So now the current is flowing through here is 10 times smaller. So I have less power dissipation. Why would I care? Well, this supply voltage might be a 9-volt battery. So now if I make the amount of standing current less, then the thing can run longer on a standard battery. Yeah, all of these are degrees of freedoms that you get to play with when you're doing analog design. Okay, so here's my gain. And if we had 100 millivolt input, then we get 7.5 volts on the output. Okay, that's the other question.
I got one. Oh, what's you see the gain, the voltage gain right here after the equal, before the equal sign? What does that say?
Well, here,
Go down right there, the one before the equal sign. What did that say?
oh,
What's the zone?
those are magnitude, absolute value, because there's actually a negative sign here.
So it's the same as the one above it.
Yeah.
Okay. And on this RB over here, beta and RB, can you tell me how you got 3.01? Because I got 3,000.
That's 3001.
Okay. Okay.
Yeah.
Just make it.
3.01K is 3001. Actually 3010. So we're off by about 10. Did they answer your question?
Yes, sir.
Okay. Okay, so let me point something out to you. I typically use engineering notation. So rather than writing, oh, it's 3000 ohms, I write it's 3K.
Okay. So where you get the one from?
That's my round off. Because I had see, RE was 15. I may have just made a mistake. Yeah, I think I just made a mistake. Yeah, because this 15 times 200 should just be 3000.
So would it just be 3?
Yeah, it'll just be 3 then. But it's 10. So mine has an error of 10 out of 3000. How big is that? Not much. But it was a mistake. I think, I don't know, not sure why I put that 1 on there. I may have been thinking about something else. But yeah, 15 times 200 is 3000. But let's see. So mine was, I said 3010. And the real answer is 3000. So I was off by 0.3%. So that being off by 10 out of 3,000 really wasn't that big of a deal. But you're actually right, it should be 3,000. I don't know why I put the 10 in there.
Okay.
What did you say that beta was, Mr. Bells? I see the RE was 15. What was beta?
200.
Okay, 200. Okay, I ain't look up there. 200.
And again, I normally would not just write the answer. I would normally write the equation, substitute in the 200 and the 15, and then say equals 3K. Okay. So now, before we go much farther with your calculating our Thevenin's equivalent resistance at pole location, let's look at our gain right here. So our gain now is basically 75.4. That's magnitude. So a voltage gain, 75.4 volts per volt. I want to convert that into decibels. And the definition of decibel, how we calculate it, is going to be 20 times the log base 10 of, in this case, 75.4. And this is also in your reading material. What is it? Log. Gives me a 37.5 dB, which is a little different than what the book has, but oh well.
Excuse me, Dr. Belzer.
Yes.
Will we be able to access the recording of this meeting after the class is over with as well?
Yes, I will. After I convert it, I'll send it out to the class.
Okay, thank you.
So we got now, this is our gain in decibels or dB. The reason I'm mentioning this now is that when we're done with our poles, calculating our Thevenins and then calculating our poles, we're going to plot our gain. Oh, this is referred to as our mid-band gain. Okay. And let me just go ahead and mention this briefly. So we have the gain here in dB, and we have a logarithmic plot of our frequency here. We're going to end up with, this is, we'll call A mid, over this wide range of frequencies. Our gain is not going to change a whole lot when we calculate it to dB. Now it's actually changing. It's not staying flat. But when you convert it to dB, then you don't see a whole lot of change. It's going to look relatively flat until you get to your pole frequency here and your pole frequency here. And then it'll start dropping off. So what we just calculated is our mid-band gain. And where we're going next is where are our poles. There's actually a pole due to CE, your CE capacitor, poles due to CC, your collector capacitor, and a pole due to CB, your base coupling capacitor. Each one of those shows up here somewhere. And I can sort of tell you This guy is going to be FL. So this is where we're going with this. We have our voltage gain already. Now we need to calculate our poles. And once we calculate our poles, we can put our A mid here. We can put our poles down here on this particular frequency. And then we can draw our lower part of our frequency response. Okay. This will be here. Now, if we go back, let's see if I can do it this way. Yeah, let's try this. Earlier in the class, we wrote what our Thevenin's equivalent resistance is for our C sub E, C sub B, and C sub C. Here are the expressions. Okay. So I'm just going to copy these over to the next page and plug the numbers in. And then we're going to calculate from there. So let me rewrite this one. And I'm not going to redraw the small signal model. So we're still doing small signal. Come down. Frequency response. So for our CE capacitor, which is 100 microfarads, our R Thevenin CE is going to be RE in parallel with little RB plus our source resistance RS in parallel with big RB, which is R1 in parallel with R2. So here we're going to get, and you have to refer back to, well, you can refer back to the book, I guess. RE is 1.5K. It's RE, low RB then is 3K. You can get that from the previous page. Plus, our RS is 1.5K in parallel with RB, which I think was 6K. Now let's see if I can calculate this. So 1.5 in parallel with 6 is going to be small. So this is going to be 1.5K in parallel with 3K plus 1.2K. And that's 1.5K parallel with 4.2K. See. So this is 1.45K. Let me try that again. I thought it would be lower.
1.1.
What do you have?
1.1.
Okay, that makes more sense. 1.1K. I'll take your word for it. That's my R Thevenin CE capacitor. And so then my pole is going to be 1 over 2 pi R Thevenin CE times CE. 2 pi is 6.28. 1.1K and 100 micro. 10 to the minus 6. Let's see what we get here. 1.1. Hmm. It's a different number from the book, but which doesn't necessarily mean anything. The book might be wrong. I'm gonna stick with my numbers. So let's do this again. That's 6.28 enter 1.1 6.3 times 100. Yep, I'm getting 1.44 hertz.
You ain't gonna raise the 10th one. Well, I think that's the hundreds to the fifth, or just gonna keep it just regular.
I did 100. Hold on, make sure I didn't get that wrong. 1 second. 100 exponent 6 negative. Enter. That's 100 micro. 1.1 exponent 3 times 6.28. Still getting 1.5.
1.45.
Yeah, 1.45.
Yeah, that's what I got too. 1.45.
So would you want us to round it or just keep it the same?
Either way, one or two decimal points are fine. 1.45, 1.46. The most important thing is, do you know how to set the problem up? If I have 1.44, so my calculator has 1.4476. I don't need 4 decimal places for a frequency. So if you did 1.45 or 1.4, I'm okay with it. 1 or 2 decimal places is more than enough. So that's my R7 seen by my CE capacitor. We just plug our numbers in, and we've already done all the calculations before. That's why I was going through, if I go here, and doing a lot of this stuff here, because I already knew we are going to need it early, knew we are going to need it later. So I just went ahead and calculated it. Now let's look at our CB capacitor and our R Thevenin to C sub B. Oh, CB is 1 microfarad. Excuse me. This is RS plus RB.
6.
What you got? 6?
No, I thought you were saying what was the RB?
Oh. No, RS now is what, 1.5K? And our RB, which is R1 in parallel with R2, is 6. Okay, that's what you're saying. Which is 7.5K. And so then our frequency, our pole location, C sub B, 2 pi, our R is 7.5K. Capacitor is 1 micro. Which you can write as 10 to the minus 6. So that's 6.2. And so I'm getting 21.23 hertz.
When you put that 1 milliohm in the calculator, how did you do that?
1 e to the minus 6. Yeah, 1 times 10 to the minus 6, or 1 e to the minus 6. Let me there you go. So I do 1.
Is it 6 or 3? You had 3 up there.
3. No, that's my C sub B value. It's my micro. So let me slide this up. Let's see, you can see it okay. Oh, maybe I'll hit it. So what I did it was 2 pi, which I know is 6.28 enter. Oh, let's clear that. 6.28 enter. And then 7K, 7.5K, 7.5 e to the 3 times 1 e to the 6 negative times enter. And I take the reciprocal of it. I get 21.23.
So you did 7.5 to the E2?
E3.
Yeah, 7.5 E3.
K.
And then, huh?
7.5K is 7.5 E3. That's the third. That's 10 to the third right here. This is 10 to the minus 6. Okay, where are you getting hung up at?
Trying to calculate it. Because I kept getting 21,000, well, yeah, 21,220.
Yeah, that's what I'm getting. But I'm getting it in a 0.021.
I had got that one at first, and then I put what I do. I had put the little 1 times 10 to the 6, and then I had got 21. I had got 21,000.
Yeah.
So
That was just not putting 100.
yeah, I'm calculating the denominator, which is 6.28 enter 7.5K 7500 times 1 micro is 1 times 10 to the minus 6 1 E6 negative times 1 over that. Of course, my calculator is reverse Polish notation, so I put things in a little differently. Which is kind of weird because I'd never done reverse Polish notation until I was in grad school. And once I got this calculator, actually, this is my phone with an app on it that looks like my calculator I used to have. It's a HP, what is this? So the 42S. So what you're telling me is we need some practice learn how to work out calculators.
I'm trying to figure out where you was getting the 3 and the 6 from. That's what I was trying to.
The 3 came from here, 7.5K. That's 7.5 10 to the third.
Okay. I see what you're doing. So 10 to the third.
And the 1 micro is 1 times 10 to the minus 6. And so I in my calculator is 7.5 E3.
Right.
And here it's 1 E minus 6.
I got it now.
Yeah. So let me ask you, so if we get it in that decimal form, would that be wrong? If we put the 0.02122?
I wouldn't be wrong, but you're gonna lose some points.
Okay.
So that means it's wrong.
No, it means I'm penalizing you for not putting in an engineering notation, which you should know how to do. And if you're not there yet, you need to get there. So the purpose of doing scientific notation, which engineering notation is a subset of scientific notation. And you use scientific notation when you're writing very large numbers or you're writing very small numbers. You know, if I was writing 10 million, at some point I get tired of writing 1.10000000. And so instead of doing 10 million, 100 million like that, you go what? 1 e to the 8. And so that's scientific notation. The purpose is so you wouldn't have to keep writing all these zeros. And then engineering notation is a subset of scientific notation. Because we're only going to deal with factors of 3. 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12, 10 to the third, 10 to the 6th, 10 to the 9th. So we're just taking part of the scientific notation and only dealing with the ones that are factors of 3. That's why we talk in terms of milliamps as opposed to, 0.001 amps. We'll just say 1 milliamp. You don't have to write all those zeros. We get down to microamps. Are we really going to write 0.000001 amp? No. We're going to write 1 microamp or 1 e to the minus 6 amps if you're going to do it in amps. But you're not going to be writing all those zeros out. That is for arithmetic. We are engineers. So, I'm not trying to call anybody out because I've had people ask these questions before. Learn how to use your calculator. The reason I use this particular app that emulates this HP42S is because I used it for years. And so I'm very familiar with how to use this calculator. You need to do the same with yours. Now, I have probably about, I don't know, 7 or 8 different calculators around here. I have another HP42S. No, that's HP48G, which is a lot bigger than this one. You enter stuff the same way because it's reverse Polish notation. And then I have a bunch of other calculators like, see, what is it? I have an OTI 55-2. I have a Casio. I have a Sharp. But I use this one because this is what I'm familiar with. So you have to get familiar with the calculator that you have. So if you need to go and play with some stuff, excuse me. So we're calculating what the answer is. So now you need to figure out how do I use my calculator to get mine to look like this. Okay. Any other questions? All right, let's do this last poll here. And this one still, yeah, this C sub E still bothers me. Let me take a look at that. Maybe something's not right there. Anyway, that's C sub E, C sub B, C sub C. We have, and its value is 1 microfarad. And R Thevenin of C sub C was what? RL plus RC. If I remember correctly. Oh, here it is. Yep, RL plus RC. And RL and RC are 3.6K and 4.7K. So this is 4.7K plus 3.6K. Oh, that's that 0.3. That's a K here. Was it 8.3?
Yes, sir.
So R Thevenin, seen by your C sub C capacitor is 8.3K. Then my pole, F sub C is 1 over 2 pi. R is 8.3 K. And my C is 1 micro. Or 10 to the minus 6. So what do we get here? 6.28. Looks like about 19.19 hertz. Sorry.
And I had redid that first one for you.
And you still get this?
I got 144.75.
Okay. I actually like that one better. It makes sense. 144.75.
Yes, sir.
I don't know if it's right, but it's reasonable. Here's why I say that. Having done these problems before, and these types of problems before, this guy right here is always the larger number. And it should make sense that he's the larger number because he has the smallest resistance here and here. Of these three, he has the smallest resistance, which would make this larger, even though this is 100 micro. And see, that's I think what's throwing me off. Let me make sure I got that right.
When I had asked you about the E to the 10 to, I didn't do that on that one. So that's why I was so wrong.
Okay.
Didn't do that one.
I may have made a mistake in punching the numbers in too, but this one should always be the highest frequency. They don't know if it's right, but at least it's consistent. Okay, so now we have our 3 poles, and we've calculated our gain, and we converted our gain to dB. So let's look at plotting this. And then I think we're going to shut it down. Here is frequency. Here is our gain in, what was it, 37 dB, I think it was. A little different than, like I say, not sure the book is even right. Sometimes the answers are wrong in the book. Oh, here we go. So our gain in dB is 37.5 dB. So here's the magnitude of our gain, dB. This is 37.5 dB. So somewhere up here, the gain starts to drop off. We don't know where that is. We'll deal with that next time. But the low frequency, we have 3 poles. We have one pole at 140, basically 145 hertz. We'll say it's here. And this is your F sub CE. So at this point right here, our gain starts to decrease at a rate of minus 20 dB per decade. Now, what does that mean? A decade is a factor of 10. So if we had no more poles down here, and this is 145 hertz, 1 decade below that is basically this divided by 10, which would be what?
0.
145 divided by 10. Frequency
14.5.
be 14.5. So over here somewhere at 14.5, well, no, let me do it down here so I don't mess this one up. We'll just deal with this just for 1 second. So if we had a pole, and I know I'm off the screen a little bit, that's intentional. We're gonna plot just this one. So we're here at 145 hertz. And we're over here. And I'm going to cheat and just make this 40 dB. Let's say our mid-band gain is 40 dB. And so here is my first pole that starts to roll off. It rolls off at a rate of minus 20 dB per decade of frequency, where decade is a factor of 10. So down here at 145 divided by 10, or 14.5 hertz, our gain would be down by 20 dB. 20 dB down from 40 is 20. So 1 dB down, excuse me, 1 decade down in frequency, my gain has decreased by 20 dB. So this will be 20 dB. Another factor of 10 down from this, which would be what, 1.45 hertz. We're down to 0. So here is 20 dB per decade. Here's 1 decade, decrease 1 dB. Here's another decade, which would decrease another dB. And so now we're down to 0 dB. Now the textbook does a little analysis and explains to you, or shows to you why the roll-off is 20 dB per decade. I'm just going to tell you that it is, and we're going to use it. Normally this would, well, when I was a student, this is called a Bodie plot, and this was covered heavily in AC circuits. So we did a lot of this before, long before we ever got to electronics. So over here, we had 20 dB per decade slope for this first pole, which is F sub C. Our next pole in frequency is at 21.23 hertz. So if we went down 1 dB from here, excuse me, 1 decade from 145, we'd be 14.5. Let's see, we're here. This would be 14.5. However, before we get 1 decade down from here, we encounter a second pole at 21.23 hertz. So somewhere up here, we have another pole. And this is the one due to F sub CB. So when I have another pole kick in here, that changes the slope again by another 20 dB per decade. So it does this. The slope gets twice as fast because now I have 2 poles here. And then we have the third pole due to F sub C, which is at about 19 hertz, which is not really far away from C sub B. So it's about here. And that makes it decrease another 20 dB per decade. So it's going to roll off at, it was 20, now it's 40. Now it's going to be 60 dB per decade roll off. So each pole gives you 20 dB per decade roll off. This is 1 pole here. 2 poles will be twice as fast. 3 poles will be even faster. So if I want to make this look like a brick wall or a square, I need a lot of poles all at the same place. So 1 pole looks like this, 2 poles look like this, 3 poles look like this, 100 poles look like this. And we'll talk about this roll off or this shape more when we get to filters later in the semester, where you actually want it to roll off fast. So here's our Bodie plot. And it's named after an Englishman by the name, I think it's James Bodie. So I plot my first pole here. So we're here somewhere in mid frequency, and we start decreasing frequency, and we hit a pole here. This first pole we hit, we call F sub L, our low frequency pole. And that is our dominant low frequency pole. Dominant because it kicks in first. And then we have these other poles that'll kick in. They'll change the shape further out here. So our F sub L is our dominant low frequency pole. And in this case, for this particular amplifier configuration, is usually caused by your C sub E capacitor. That's your low frequency pole. Okay. And we'll look at some more of this next time. Before we get together again, look at example 9-2 on page 363. So it basically takes this, another problem, very same configuration, and it basically walks through everything we just did here. Okay? But you need to be familiar with this flow because this is what you're going to be expected to do. Any questions? Or comments?
Please don't forget to upload that video, Mr. Bells.
It won't even, okay. It won't even start to convert until I shut this down.
All right.
Once I end this, it'll start converting automatically.
Okay.
So,
Will you have the video before next class?
well, it should finish in probably less than 10 minutes. I'll send it out tonight.
All right, cool. Thank you.
Hopefully it doesn't get too big. All right, but if you haven't gotten it by tomorrow, ping me, just in case something happens.
All right.
Okay. All right, that's all I got for now. I guess I'll stop sharing. And let me do this. One thing here. Oops, come back. Unshoe. Ah, there we go. Snippet. Send to myself, I guess. So I'm basically taking a picture of the enrollment because I have to. Oops. No. File. Save as. All right. Yeah, but if I plan on sending it out as soon as I finish converting, which usually takes less than 10 minutes. Depends on how big it is. And if you haven't gotten it by tomorrow, let me know.
All right, will do.
All right. Have a good evening, everybody.
All right, you too.